Welcome, everyone. In this lecture, we begin with a fundamental idea in statistics: uncertainty. In real life, managers, researchers, and policymakers rarely know outcomes with certainty. Sales fluctuate, exam scores vary, customer wait times differ, and even human behavior is unpredictable. Statistics exists to help us manage uncertainty using data. Instead of guessing, we use probability models to describe what is likely, what is unlikely, and how confident we are in our conclusions. Today's focus is on probability and the normal distribution, which together form the backbone of most statistical methods you'll use in research, SPSS, econometrics, and hypothesis testing.
Why do statisticians care so much about the normal distribution? Because nature, society, and organizations tend to behave in patterns. When we collect large amounts of data, heights, IQ scores, delivery times, errors, or satisfaction ratings, we often see the same smooth, bell-shaped pattern appear. This distribution allows us to calculate probabilities, compare individuals to the average, and test hypotheses scientifically. Without the normal distribution, modern statistical inference would not exist. Statistics is not about being 100% sure. It is about making decisions with confidence based on probability and data.
Let's make this concrete. Think about exam scores. Most students score around the average. Fewer score extremely high or extremely low. The same applies to employee performance, reaction time, daily sales, or manufacturing defects. These patterns are not random chaos. They form a predictable shape, the normal distribution, which allows us to analyze and interpret data systematically rather than emotionally or intuitively.
The normal distribution has three defining characteristics. Symmetry: the left side is a mirror image of the right side. Mean equals median equals mode. All measures of central tendency coincide at the center. Most values cluster around the center, and extreme values are rare. This is powerful because once you know the mean and standard deviation, you know almost everything about the dataset. This simplicity is why the normal distribution is so widely used. Probability is simply a numerical way of expressing uncertainty. It always ranges from 0, impossible, 1, absolutely certain. For example, the probability that the sun rises tomorrow is very close to 1, while the probability of flipping a coin and getting both heads and tails at the same time is 0. Everything in between reflects varying levels of likelihood.
Some probabilities are exact, others are estimated. A coin toss has an exact probability. Heads equals 0.5. Tails equals 0.5. Business outcomes, such as market success or customer churn, rely on estimated probabilities based on historical data. This distinction is important in research. In social sciences and management, probabilities are almost always estimated, not known with certainty.
A fundamental probability rule is P plus Q equals 1. If an event has only two possible outcomes, such as success or failure, then the probability of one automatically determines the other. For example, if the probability of customer retention is 0.7, then the probability of churn must be 0.3. This rule underpins hypothesis testing, confidence intervals, and decision-making under uncertainty.
A single coin toss is unpredictable, but when we repeat the experiment thousands of times, patterns emerge. This phenomenon is explained by the law of large numbers. As sample size increases, observed outcomes converge toward expected probabilities. When many random processes combine, their results often approximate a normal distribution. This is why the bell curve appears everywhere.
The empirical rule is one of the most practical tools in statistics. 68% of values lie within plus or minus 1 standard deviation. 95% lie within plus or minus 2 standard deviations. 99.7% lie within plus or minus 3 standard deviations. This allows quick, intuitive interpretation. For example, if the average exam score is 70 with a standard deviation of 10, then about 95% of students scored between 50 and 90. No advanced calculations, just understanding the pattern.
A z-score tells us how far a value is from the mean in standard deviation units. Z equals 0, exactly average. Z equals +1, 1 SD above the mean. Z equals -2, 2 SDs below the mean. Z-scores allow us to compare observations from different scales, test scores, income, productivity, on a common metric.
Z-scores connect data to probability. Z equals 0 equals 50% of values lie below. Z equals ±1 equals about 68% lie within this range. Z equals ±1.96 equals about 95%. This is the foundation of confidence intervals, hypothesis testing, and statistical significance used in SPSS and journal articles.
Consider a telecom company monitoring call duration. If average call time is 6 minutes with a standard deviation of 1 minute, and a call lasts 9 minutes, that is a z-score of +3. According to the normal distribution, such calls are extremely rare, less than 1%. This insight helps managers identify anomalies, improve staffing, and detect potential issues using statistical reasoning rather than intuition.
Before applying parametric tests, it is essential to verify whether the data follow a normal distribution. SPSS provides 3 commonly used tools for assessing normality. Histogram allows visual inspection of the data distribution. QQ-plot, data points should closely follow the diagonal line. Shapiro-Wilk test provides a statistical test of normality. Understanding and correctly applying these tools is critical for conducting credible research and meeting journal publication standards. Comment below if you would like us to upload a step-by-step video on how to verify normality in SPSS. To conclude, probability quantifies uncertainty. The normal distribution explains real-world patterns. Z-scores standardize comparison. Significance testing separates signal from noise. Mastering these concepts will strengthen your ability to conduct research, interpret SPSS output, and publish confidently. If this lecture helped you understand probability and the normal distribution, please like, subscribe, and share. Comment below if you'd like a dedicated video on degrees of freedom, confidence intervals, or hypothesis testing in SPSS.